talk about how to achieve this level of security. So there's provable security if you have some kind of mathematical proof, and then there's heuristic security, which means when people just try to break in, they can't get in. So provable security, it would be nice to have a mathematical proof that it's perfectly secure, but like I say, except for the one-time pad, nobody has that. So instead what you do is you relate it to another problem. That you can do. So RSA requires factoring number into its component primes. Now that has been a problem people have tried for about 2,500 years to solve, and nobody's found a very good solution. So we have some degree of confidence that that's a really hard problem. So that's one thing. So we really don't know that it's hard. And by the way, so it'll come back later, this is the whole issue of whether P equals NP. There may be no hard math problems at all. It could be that all math problems are easy and we just haven't found the easy solution yet. So that's the issue of P equals NP. Are there really any hard math problems? Or are there just ones where we haven't found the shortcut yet? Most people believe there really are hard math problems that cannot be solved easily. But there's no proof of that. And there's a whole bunch of people trying to prove that there are really hard problems that can never be cracked, and that has not been done yet. So you have to settle for a less degree of proof. So anyway, the prime number, if you believe that factoring numbers into their component primes is a really hard problem and no shortcut is going to be found, then if you can prove that your system is as hard as that, that would be pretty good proof. So here's the RSA algorithm. Choose two random large prime numbers, multiply them together, then you choose an exponent e, you usually just use this constant number, and that's the public key, n and e. Then you encrypt your data with the private key. So to encrypt it, you encrypt it with e, x to the e mod n, and that gives you a number. You have a message, which is x. You raise x to the e mod n, and that's the ciphertext. And in order to decrypt it, you have to take y to the d mod n, but d is the decryption key, and you can only find that if you know p and q. But the public key, people only need n, and so they can't find the decryption key unless they can factor n into P and Q. This is the RSA algorithm, which was used for a long time to secure everything on the internet, and is still used, although these days it's mostly less popular because it's just more expensive to implement than elliptic curve cryptography, which came later. But this was the first popular public key algorithm, and this has been working very well, but it fundamentally rests on the fact that even though everybody knows n, they can't find P and Q. So it's hard because the factoring problem is hard.
E is public key, right? E, the customer has E.
Yeah, you publish E and N. Yep. So you know the encryption key and you know N, but you can't reverse this process.
This works only in one way, right? The one-way encryption.
It's only one way, which is the problem. The fundamental problem with all public key systems is you have to make a private and public key, and now you can receive messages, but you cannot send messages. The person at the other end has to make a private key pair, and that is not easy. That's the weakness of it. But you can receive secrets, and therefore the person at the other end does the same thing. Then the two of you can exchange data with great confidence. Good? All right, so you try to compare one cryptographic scheme to another, and you can prove that you can only break the new one if you can break the old one. This is how you derive new schemes, and you make them as secure as the old one. So we develop symmetric algorithms, random bit generators, hash functions. They often base these on known algorithms that they know are hard. So you know that the new thing based on it is going to be as hard. So, and that's essentially what's going to happen. AES, for example, and all the schemes basically try to create a bit stream like a one-time pad from the key. That's the idea. But they're not perfect at that, so none of them are secure as the one-time pad. All right, so the underlying system might be broken. Like I say, you might find some shortcut, which is what happened with WEP. Had 104 bits, but it turned out you didn't really need to try them all. And the mathematical proof might overlook something or have an error. So RSA is easy to crack if P and Q aren't sufficiently random. And this has turned out to be a big problem in practice. A whole bunch of RSA keys used on the internet turned out to be crackable because P and Q were not random. They didn't have a good enough random number generator. Knapsack is another algorithm. It was totally broken by lattice reduction, and this happened to most of the proposals post-quantum cryptography. They started out with 14 proposals, and I think several of them were completely hacked to where you could totally get in. They found a weakness in the math where you could punch right through, like WEP. this happens. That's why the current procedure is very good. The NIST announces a contest, and then they take submissions for years, and then they have years of evaluation where people hack each other's submissions, and only after that long process, like 5 or 8 years, do they find an algorithm which they then will stamp with the US government seal of approval saying, this thing seems really secure. And that's worked out. The approved algorithms, so far none of them have been found to contain serious flaws. But it certainly could happen. And of course, side channel attacks could break in, which are not mathematical, based on radio waves, power consumption, timing. The actual implementation of it in hardware can have flaws, which are not because there's a defect in the math, but it still amounts to the same thing. People can get in your secrets. And so this is what I found. You know, when I analyzed all these Android apps, I analyzed hundreds of them, and most Android apps just implement cryptography incorrectly. So even though they use a system which is perfectly fine, like AES, they implement it incorrectly, so the key is just lying around somewhere, so you can just find the key.
These shouldn't be handled by Android apps.
What's
The
that?
Android system should handle encryption, right?
Yes, Android has an encryption thing called the key vault, and they just don't use it. Instead, they invent their own system, which is garbage. It's ridiculous. It seems to be the standard for app developers. They've just gotten in the habit of doing this stupid thing, which is what happens for most cryptographic failures. There are just traditions of doing something stupid which get entrenched. Like until about 15 years ago, everybody would just put a hard-coded administrative password in there that they regard as a secret so that tech support can help you. And it took a long time for them to realize that's not a good idea. If you watch the movie Tron, the guy makes a computer system and then he gets sucked in it, and his son comes around 20 years later. He says, oh, Dad always has this backdoor account with this password he told me to get in. That's the way it really was until about 15 years ago. All technical devices had this. And like 2 years ago, there were 8 vulnerability reports in a year of Cisco devices where they found the backdoor password. They were doing that in everything. This was really common practice. And that's the thing. People get a stupid tradition and they stick with it. And the Android apps seem to have established as a standard encrypting stuff with AES and then hiding the key on the device. But I can see the source code, so you can't hide the key. But they don't seem to know that yet.
Hard-coded password is now used as a honeypot.
Yes, that's true. Hard-coded password. This is a little bit different than a hard-coded password, but they would calculate it, but you can see the algorithm. But yeah, essentially hard-coded password. Anyway, so yeah, using it as a honeypot would be a better use for it. Anyway, so then there's heuristic security. So symmetric ciphers typically don't have a security proof. So what they have is this. Like I said, the process of NIST. They announced it. They invited a contest. A bunch of advanced mathematicians tried to get in and failed. That's how secure it is. How secure is that? Well, you know, that's how secure it is. It could very well be that like enemy spy agencies did get in and didn't tell us, and we would never know. But the public mathematicians that were willing to try did not get in. So that gives you whatever security that gives you. So then you can have a security margin. This is often what you do. So cryptanalysts often look at a simplified version of the cipher, and they can get in that, but they can't get in the full one. So you try to take the one that no one can get in, and then add some more layers to it, and say, there's my margin. So that's the problem. This is what you call your security margin, the difference between the one that they can crack and the one you're using. So AES, for example, the main one we're using, it's got 128, 192, and 256-bit keys. And they differ in their key sizes and their number of rounds. It turns out in AES 128, nobody has found any shortcuts. It really takes 2 to the 128 calculations to get in. But AES 192 and 256 do have weaknesses. You can break in AES 192 with only 2 to the 176 calculations. And you can break in AES 256 with only 2 to the 119. So it's in principle the weakest of the three. So now all those are over 100, so they're in practice uncrackable. But that's why, from a purely mathematical point of view, AES 128 would be the most secure. But because they found a shortcut in 256 to lower it down to 119. But remember, the quantum computer is going to completely destroy this one and not that one. So if you're worried about a quantum computer, this would still be the best choice.
So 256 is actually easier to solve than 180 or 128?
256 has a 256-bit key,
Yeah.
and a quantum computer could break it in 2 to the 128 calculations.
No, I mean
But the shortcut can get it down to 2 to the
So
119.
it's actually easier than the original.
Yes, weaker than this one. in practice, except there's more to it than that. This was a weaker version of 120, or 256. That it only cracked 11 rounds of 256. The full AA6 has 14 rounds. So, however, that's worrying. That makes it seem like it's really not giving you 256 bits of security. It's giving you something less, and they estimate 119.
AES use random the prime numbers?
No, it does not use prime numbers. The key is just a random number. Does not have to be prime. So you have 128 bits, just random. That's all.
I thought the quantum computer is used for prime numbers.
No, the quantum computer, there's a Shor algorithm, factors prime into prime numbers. There's another algorithm, I forget the name of, just to attack AES. And that has the property of it takes 2 to the 64 cycles to break 2 to the 128. So there is an attack against AES on quantum computer, just like there's an attack against RSA on quantum computers. But the RSA attack is much more devastating. They say the RSA attack, if you had a good quantum computer, no length would be good enough. Not even 1 million bits, not even 10 million bits. You could crack them all. The AES attack is not that powerful. It only takes you down to the square root of the number of guesses. So it should not work on AES 256. This is what I learned at the Cloudflare Summit with the cryptographers from Berkeley. They said, so if quantum computers come, we'll have to abandon all current public key encryption schemes. They will all be destroyed by quantum computers, but private key encryption is not destroyed. You'll just have to double the number of bits. So if you just move from AES-128 to AES-256, we'll be okay. That's why they had the contest, which I think just finished, to develop quantum-resistant algorithms. Our public key systems are all going to be abandoned in the next few years and replaced by quantum-secure cryptographic systems. All of them are going to be cracked. They're worried about the development of quantum computers, and they have developed new algorithms that can resist quantum computer attacks. And we'll all be switching to them over the next 5 or 10 years. I would like to put them in your projects, but when I tried to add them last year, the one I was going to add was Google's New Hope, and right when I started doing it, they cracked it and abandoned it. So I said I better wait till they finish the process. But I think they have. I think they had an announcement recently. So hopefully I can add to your projects quantum-proof encryption. That's where we all have to go. But I haven't done it yet. Anyway, so generating keys. The simplest way is to generate randomly using a pseudo-random generator. You could generate it from a password using a key derivation function, or you could use a key agreement protocol like Diffie-Hellman to agree on a key between multiple parties. These are various ways that are used to generate keys. Symmetric keys like AES-128 just are simple random numbers, just like coin flips. And there's a bunch of random number generators like OpenSSL has one. And then you can worry about how random it is. But anyway, that you find a random number generator, you generate 16 bytes, and that's a 128-bit private key. Now, for asymmetric keys, for RSA, it's not easy. What you have to do is you have to find random large prime numbers, and there is no algorithm that does that very well. What there are algorithms that can detect when a number is not prime with a certain probability, like 50%. So you guess random numbers, and you check to see if they are not prime, and you repeat that like 10 times. Now you have pretty high security that that number is prime. And if it's not prime, you guess again. That's how you do it. So the result is generating a private key is extremely fast, 16 random flips. Takes almost no time at all. Generating a public key takes a really long time. Let me just do this live. This is good, clean fun. So if I clear, okay, you can easily do it in Python. So if I do Python 3, all right, and then from crypto public key, import RSA. Oh, I don't have it on this machine. How rude. I may have to import it. Let me see if I can find, there's a name for this library. Let's see, I may have to put this live demo off to next time. It's in various places. Let's try, this is the kind of job that ChatGPT is good at.
I mean, attackers can pre-compute the prime numbers too, right? They can have table prime numbers like that.
Attackers can what?
Pre-compute the prime numbers.
No. Well, they can pre-compute it, but that's useless. I mean, you have a random prime number. They have to find the one you used. They can generate their own random prime numbers.
N is published, right? N is public. And no,
N is public.
N is the second one. Second prime number is public too. Or no?
Just N. So you have to find P and Q, and they're both secret.
Oh, okay.
Yeah, if you have one of them, you got the other. So here we are. This is the error.
Implies,
Pip install crypto. Yeah, there's another one besides crypto that I'd like to use. This is the one. I thought it solved this. PyCryptoDome. That's what it is. This is what I couldn't remember. So I need to install PyCryptoDome. And let's keep asking ChatGPT how to install PyCryptoDome in Python 3. I thought I had it on this. Oh, this is my new machine. That's why. So let's find out how to do it. I think it's just pip install PyCryptoDome. Yep, it's pip install. So ChatGPT was good for that because he's just looking up the documentation for me. So this should do it. Let's exit and pip install PyCryptoDome. And all right, you don't have pip, but I know the cure for this. Somebody who knows Python better than me can figure out why I have to do this, but I just learned you have to do this there. All right, now I've got it. Now, if I run this, I should be able to, there, from crypto, there we are. Now I can do some key generation. So, key is RSA generate. So key equals RSA dot generate. So let's start with 512. 512 is the way the original RSA was published in 1979. They said 512 bits will be enough. And you can't even, it won't even let you do it anymore. That's no longer considered secure. But that was considered secure in like 1979. 1024 is the shortest. Okay, it came up right away. If I do 2048, it took about 2 seconds. If I go to 4096, 1, 2, 3, about 3 seconds. And if I do 8192, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It'll take a long time because it's having to make numbers that are 4,000 bits long randomly and check to see if they're prime. And then that fails, so it has to try thousands of times to find a prime number, and then it has to do it again. So it's amazing that that's the process, but that is the process, and you'll be doing it in the projects. That's why it takes a good long time to generate these, because it's a very clumsy process. Anyway, after that, you generate a key. Now you have to protect the key, so what you typically do is wrap it with a second key. So even if somebody can come up to your machine and type on it, they can't get your key because there's a password protecting the key. So this is how you wrap RSA keys typically. And now if you generate the key from a password, you don't need to store it anywhere at all. And this, by the way, is a much better solution for encrypting on a phone. You encrypt it with a password, and you don't store the password anywhere. So the only way to get in is to know the password. This is why, this is the best way to do it, really, for humans. Then you have to remember your password. Then the only problem is humans might choose a foolish password that's too short or something. All right, anyway, but this is a technique that's used a lot, and we'll play with that, key generation from a password. So here's things that can go wrong. All right, good. So you might have a bad proof. Your proof might have flaws in it. RSA's padding, this form of padding we'll talk about later, was proven, and it turned out the proof was wrong, but it turned out it wasn't wrong in a terrible way. It was in fact secure anyway. But that can happen, of course. You're mathematicians. This is a thing. When I first learned math, they said there's this thing called a proof from fundamental principles. It has only been done for about a dozen mathematical algorithms where you actually prove everything right from the fundamental axioms. This is incredibly painful, and you almost never do it. All real math is you write a paper and you make it sound good enough that you convince other mathematicians. But nobody ever proves it from fundamental principles. That's why when I was a kid, I thought math is like perfect. And when you learn it, it's not that perfect at all. It's no more perfect than any other human endeavor. I thought it's really just kind of like, public policy. You say something, convince other people, they agree with you, that's what you go with. It's a little better than that, but it's not as perfect as I hoped it would be. And then you get Gödel, that proved it can never be perfect. That's what really blew a hole in it. When I was a kid, I thought math was perfect, and Gödel proved that no mathematical system is ever complete and perfect. If you define axioms, there will always be propositions that cannot be determined whether they're true or false from the axioms. which is pretty disturbing. That means no system is complete. Anyway, so the whole idea of mathematics being pure and perfect is in fact provably false. However, we're living with it. It's good enough to get us a lot of things done. So then there's another problem, which is politics. This is what's happening right now in the UK. The government wants to read the encrypted stuff. Now, in America, they just secretly poison the encryption scheme so they can read it, and we're not supposed to know about that. And then they leak out the secrets and get caught, like with Snowden. So that's our system. In the UK, they're sort of more honest. They're passing a law saying everybody must have a backdoor and give us the plain text for everything. And then Meta said, well, we're going to just leave your country then. We're not going to do that. And then they backed down and said they're not going to enforce it. But that's the issue. So what the US did and in the 1990s was they defined export-grade cryptography, which was weaker because they didn't want to export high-quality cryptography, which is kind of stupid beyond belief. I mean, there were public papers in the 70s defining RSA encryption. They said, well, there aren't any intelligent mathematicians in Russia or China, so if we don't sell them products that use strong encryption, they won't figure it out, which is pretty stupid. But that was the government's official position, so they could only sell broken cryptography. So they sold like 512-bit RSA on a special version of Windows called Windows N or Windows K for export. And so that meant you had to have servers that would speak that broken encryption, and that poisoned the internet to this day. There are servers that you can tell them, I'm using like export American encryption from the 90s, and therefore you have to speak old encryption. So these downgrade attacks work. So this is why the cryptographers hate this. When it's like, you know, telling somebody it's okay to sell food with poison in it, we'll just sell it to the other nations. They say, this is not going to work. This stuff is going to move around. Somebody will repackage it and sell it back here, you know. This is one of these short-term military, there's another one. The CIA did. The CIA went to Pakistan. They wanted to infiltrate terrorist cells, so they infiltrated the medical teams that were going to bring vaccines to the isolated villages. Some of the so-called doctors are CIA agents. So they figured this out. So now nobody will take the vaccine because you guys are CIA agents here to kill us. And the CIA had to apologize, said, you know, that wasn't such a brilliant idea. We
That was how the CIA tracked down Bin Laden, right?
What's that? When they tracked down Bin Laden, yeah. I don't know if they used that technique, but
Use a doctor.
they used the doctor to catch.
Track to
Oh,
pinpoint where
I-
Bin Laden.
I didn't know that, but yeah, it's a trick. Anyway, so this is the problem. You know, you use when you do something nasty enough, you create blowback later from.
Attacking AES with Grover's algorithm.
What's that?
Attacking AES with Grover's algorithm.
With Grover's, yeah, Grover's, that's it. Grover's algorithm is the quantum algorithm to crack AES. Like Shor's algorithm is the quantum algorithm to attack RSA. That's right, it's Grover's. Good. All right, let's try another Kahoot, which is here. 141 3B is here. All right. Yes, the N and the E, yes, you publish both of those. And that's because then anybody can encrypt stuff and send it to you. They need N and E to do that. That's why it's just like the mail slot in your door. There's a slot anybody can stick stuff in. Nobody can read it. Yeah, that's the idea. And traditionally, you make the E small, so the encryption process is not difficult. The decryption gets more difficult. That's typically what you do. You want to make it easy for people to send you stuff, and then you'll have to go through more calculation to read it. All right, I guess we got who's coming. All right, so what property means that experts have failed to crack in? That's heuristic security. Means the experts that we know of have not been able to get in, for what that's worth. All right, which number is the secret in RSA? P is secret, and therefore Q, P and Q are easy to, if you have P, you can find Q. And N and E are the public key, P is the secret key. All right. All right, which operation will convert a password into a key? That's key derivation, KDF. The most common technique is PB-KDF2, password-based key derivation function 2. All right. And how do you protect a key with a password? Yeah, that's key wrapping, commonly done with RSA keys. All right, there's Charles.